Good morning, everybody. I'm James Isaac, KI0KN, and your instructor this morning for Rocky Mountain Ham University. Today we're going to do a presentation on many of the battery types that we use in our hobby. We're going to start out a little bit on the basic side, cover into a little bit of chemistry and some best practices, and there's a short story behind why I ended up learning as much as I did about batteries, whether I wanted to or not. And that was a repeated failure of batteries in my boat and RV and things like that. No matter what I tried, I ended up, getting a year's worth of time on things that should last multiple years. And so I really started to dig in. So with that, we're going to go ahead and jump to my PowerPoint to start with, and we're going to try and balance this out a little bit with PowerPoint and some demonstration things, but let's go ahead and jump to the PowerPoint here. So we're going to cover, as I said, we'll start real simple here. We're going to cover just differentiation between a couple of our common types of batteries. The alkaline is the one that's probably the most well known by everybody, the non-rechargeable types that stick in our remotes and games and toys and all that stuff. An older rechargeable technology, or two technologies, is nickel cadmium and nickel metal hydride. We've got the newest player on the market here, the lithium battery, and then lead acids. And there are multiple types of lead acid batteries. And we're going to spend a good portion of our time today talking about lead acid before the break and various types of things, and then lithium after the break, because they're so very, very different. They're also the most typically used two types in our hobby. So lead acid batteries, the most typical one, like in a car or something like that, is flooded. It's called flooded because it is a liquid acid and can be spilled. And there are two types, major types of those batteries, a starting battery and a deep cycle battery. There's a third type, AGM, or absorbed glass mat, that is available in either starting or deep cycle. We'll go over some of the differences there. And then there's also gel cell. All of these lead acid batteries use the same concept, the same acid, things like that. It's just the medium inside. The flooded battery is, of course, liquid. The AGM battery has the liquid absorbed into usually a fiberglass type mat. And the gel cell is a gel. Construction. We're going to get into a little bit of the science behind these batteries to understand what we see when we charge, discharge, and store them, and why certain pieces are important to the life of these batteries. So a typical lead acid battery we use in ours is considered a quote-unquote 12-volt battery, and that is because it is made of 6 cells that are 2 volts each in series. Those cells are not usually obvious when you look at the outside of the case of the battery, but the battery is compartmentalized into the different cells, and there are terminals within the battery that do that. The positive terminal in a lead acid battery is made of lead dioxide, whereas the negative terminal is porous lead. And the electrolyte, we're going to talk about a flooded battery here first, is approximately 6 molar sulfuric acid and water. The construction is depicted graphically here with the terminals suspended inside of the inside. This would be a single cell, and this model would be 6 of them in series for a 12-volt battery. To differentiate between the two main types of batteries is the starting battery and the deep cycle. The starting battery is going to have many, many plates, the alternating plates that are within the acid, and they're typically much, much thinner. The reason for that is the more surface area that you have on the plate, the more current you can draw from the battery. However, the thinner the lead plate, the easier it is to damage the plates by warping. And they're designed to deliver a very high current for a short period. That's why we call them starting batteries. They're designed for, up to 10 seconds of heavy current draw, and then they expect to be recharged. Now a deep cycle battery, same construction. We have the same type of basic construction within the battery, but it'll have fewer plates and they are much thicker. They deliver less current, because we have less surface area, but they're thicker to resist warping. And therefore, we can drain the batteries deeper. We can use more charge held within the battery without damaging the battery for a longer period of time. To understand the challenges you face with keeping the battery healthy and to understand why the batteries can be damaged, why, there's a bunch of numbers. There's a little bit of math and a little bit of chemistry that we need to understand that happens inside the battery that will make a little bit more sense once all the pieces are put together. So we're going to start with the discharge. Okay, the discharge will have a fully charged battery. When the battery is just sitting there, there isn't an electric current flowing other than some leakage within the battery. But the connection of the electrical load allows the electrons to flow from the negative terminal through our load back to the positive terminal. This, of course, reduces the charge within the battery because we are doing work, and the voltages at the electrodes will also start to become lower. The chemical reactions are able to proceed within the battery, and the new electrons are generating the power converted to the form to drive the electrical load. And this is where there's a red lettered word here, a red highlighted word here. This is very, very important to understand as we talk about this. As the battery is discharged, the electrodes become coated with lead sulfate, and the acid becomes weaker. We are converting molecules of the acid into lead sulfate that's attaching to the plate. And there's a little graphical depiction showing our two anode and cathode submerged in the acid and the water and the acid molecules floating around. Okay, when we charge the battery, it's the opposite process, right? Connection of an electrical power source forces electrons to flow from positive to negative, and this increases the charge and the stored energy into the battery. This is again very important part highlighted in red. As we charge the battery, we are converting the lead sulfate that's coated on one of the plates into acid in liquid form in the battery, so the acid becomes stronger. And again, a quick graphical depiction of the battery there. Now, state of charge, right? So we can hook a load up to a battery and do work, pull energy out. We can hook a charger to a battery and put that back in so it's ready to go again. But we need to know what the state of the battery is so that we don't discharge it, so we know that we have enough energy to run the load that we want to, etc. So the state of charge can be determined by terminal voltage. And there are some caveats there. The internal impedance of the battery, temperature of the battery, things like that will change that just a little bit, but ideally voltage is the ultimate teller of the condition and the state of the charge of the battery. It's important to measure the battery with no load. We do not want to measure the terminal voltage with a load on it. It will not give you the correct answer. State of discharge. Now this is what surprises some folks. Look how small of a change we have between charged and discharged. So the acid level changes, right? We're about 6 molar to 2 molar. The specific gravity changes, but look at the battery voltage between a charged battery and a dead battery. It's 1 volt. How many times have you seen your car battery at 10 volts or the things that's something way outside of that. Of course, there's an exception, right? If you're drawing a heavy load from a battery, it can temporarily get to 10 volts. But if the open terminal voltage, no load voltage on the battery, is outside of this range, you are doing damage to the battery. If it is below 11.7 volts with no load, you are doing damage to the battery, or you have done damage to your battery. Okay, what are some of the best ways you can kill your battery? Well, starting batteries, as I said, were designed for short bursts of high load, and they are not designed to discharge heavily. The plates start to warp if you pull charge down too much in there. So 20% of your capacity in a starting battery is a good number to shoot for, to not take your battery below that. And it's about 50% for a deep cycle. As we get a little further along in here and we start looking at some capacity measurements, you're going to notice, keep this number in mind, 50%, right? So we buy a battery that's got X amount of energy available in it. If you really want to keep that battery healthy for as long a life as possible, you're only going to be able to ever use half of what's available in that battery. Leaving a battery discharge. Now this is the point that gets back to the lead sulfates that I had in there. As that discharge process happens and the lead sulfate has built on the plate of the battery, if it's left on there over time, that sulfate becomes harder and harder and harder. And as it hardens, it starts to become an insulator. It insulates the terminal of the battery hanging down in the acid from the acid. So over time, you can actually cause the battery to become almost useless because of the lead sulfate is so hard and so insulative on the plate in there that there's no recovering. Freezing is the other one, right? So we said as we discharge our battery, the acid becomes weaker and the water concentration actually becomes higher in the battery. It now is more prone to freezing. There is more water, and if it's out in the cold, it will freeze. A fully charged battery will almost basically not freeze. A near empty battery will freeze quite easily. And then overcharging. We're going to spend quite a bit of time talking about chargers in the technologies around chargers, but there are some chargers that you would really want to avoid for the health of your battery because they can boil the acid-water mix, and guess what happens when you boil it? The water turns to vapor and it leaves the battery, and the water and acid levels will drop as the water leaves, and that is the longer it's left in that state, the more chance you have of never recovering that battery. Okay, talk about the other side of the coin, the discharge. Lead acid batteries naturally lose their charge when sitting unused, and it's approximately 5% of the charge per month. The self-discharge increases though, so approximately doubles for every 18 degrees. If you use your battery for your Aries deployment, or you go out for field day and you've got some lead acids and the only time of the year you ever use them, and they're sitting in your hot garage all summer long, cold garage all winter, you will lose that battery. Its lifetime will be significantly reduced. Battery needs to be replaced if 30% of the charge is lost in the first 24 hours. Okay, we're going to talk about capacity, but before we do, I did not bring a flooded lead acid battery with me today, mainly because they're heavy. But I did want to talk about the differences. These are examples of what we call SLA, or sealed lead acid batteries. These are the batteries that have that absorbed glass mat inside of them. And the acid is soaked into the cloth inside these batteries. So one thing you'll notice on top, if you ever look at a typical car battery, they usually have plugs. And you'll notice there are no plugs on this battery. That's where the sealed part comes from. So I'm going to backtrack just a tiny bit here and talk about that process. As we charge and discharge lead-acid batteries, hydrogen gas can be generated. And in a car battery, that is typically vented through a small tube into the atmosphere. In the sealed lead-acid battery, it does not leave the battery. That's why these can be mounted in any position. You won't spill. There's nothing to spill. There's nothing to vent. Now, there are emergency vents in here. But what happens is as we charge and generate hydrogen gas, the pressure inside the battery builds. And over time, that will slowly recombine back into the electrolyte. So unless something catastrophic happens to the battery and one of the vents in the battery blows open, the gas inside the battery stays within the battery, and it will slowly recombine and bring our chemistry back to where it was before we started. So these batteries are inherently a little safer for us to use in our hobby than some of the liquid.
There's a couple of questions on Zoom here. First one from Jeff N2XGL. He says, do these concerns apply to AGM and gel also? And
absolutely. The charge-discharge rules apply to all lead-acid types regardless of what the the medium of the dielectric is.
How do you measure the percentage of charge?
We're going to get to that. We've got a full segment on that. We'll get there, and I will answer that question as we move forward here. Remember that I said voltage is the indicator for the amount of percent used of the battery. That's key, and I will address that question as we move forward here. So let's talk about capacity, right? This is a perfect question to key into here. On a lead-acid battery, we can measure capacity in amp hours, and there are so many ratings on batteries these days, and they can they can be a little bit confusing. We're going to talk about these. Amp hours is usually accompanied by a C rating, and you'll find, so C is defined as a constant current draw that will discharge the battery from its full potential to its empty potential in 1 hour. This C number exists for all batteries. However, lithium batteries typically have those written right on them. If this is a small hobby battery here, so on the front of the battery, we will see, so that is a 5.0, so that is a 5 amp hour battery, and then you'll see the C levels, they're a little bit different. This is, the last bullet on my slide there shows amp hour is actually capacity, but it is also used to describe max or charge or discharge rate. And on this battery, we have a 30C battery. We're going to get to that in the lithium section, but essentially the 30C is right here. It says 25 to 30C in that corner. And we're gonna get to that more in the lithium section, but that's on this particular battery. That is describing the discharge capability of this battery safely. So for a battery like this, where you have a 5 amp hour, you can consider this 1C would be 5 amps for 1 hour in this battery. If it's not otherwise stated, like the lithiums do, that's how you would determine that. So automotive batteries. We use automotive batteries in our hobby a lot, right? They're great field day batteries. They're great for solar setups and things like that. But you'll be hard pressed to find an amp hour rating on a car battery. Even a marine deep cycle battery, they very often do not have amp hour. So they have what's called RC, or reserve capacity. Reserve capacity is the time the battery can run at 25 amps without dropping below 10.5 volts. So the reason that number is more prevalent in automotive is we really care about how much current can the battery deliver for a short amount of time. We don't really care that the battery can deliver 1 amp for X, many, many, many hours. So the current draws are typically higher. But fear not, we can convert. RC, reserve capacity, is done in minutes. That's the number of minutes that the battery can run. So we convert that to seconds by multiplying by 60. Then we multiply that by the length of time in the RC, which is 25, and that number will give us the number of coulombs of charge in the battery. We divide that by 3,600. There are 3,600 coulombs in 1 amp. So that gives us our essentially our amp hour capacity of the battery. So let's look at this is a popular battery manufacturer that's available in our area and actually across the country. And if you look on the front of the label, we'll see RC equals 160 in this battery. So following the math through, we take 160 times 60 to get 9,600 seconds times 25 gives us 240,000 coulombs of charge. We divide that by 3,600. That group 27 size deep cycle battery right there is a 66.6 amp hour. Now, there is a little bit of change that, just like everything, there's a except, there's always a but. If you look on the manufacturer's website, they do actually list the amp hour rating on this battery at 80 amp hours. That could be rated, we don't know what C rating they were discharging at for the number of hours. We don't know what the temperature was. There can be some things that affect these numbers, even a little bit significantly, but this is a math that we can start with to get a general idea of where we're going. Now, we talked about capacity. 1C is an hour of discharge. We can use the numbers just as we would expect with the math. 2C would be the current draw to discharge the battery in 30 minutes, and a half C would take 2 hours. However, there is a law that we have to apply here called Puchert's law, and there will be a Puchert constant for any battery situation that we come across that's based on, there's the math. I'm sure if you want to squint at that and figure it out, I would say, go Google that. But there's a whole, basically what Puchert's law says is it's not a perfect world, and you're not going to get all of the capacity that is rated on there because that's a laboratory number and a lot of other things are in play. Temperature, the current draw that we use. There's a much easier way to use a rule of thumb on what your capacity is. Use 80%. Whatever the battery is, designed for amp hour wise, use 80% of that as being the total available energy in that battery. It will be a little higher, it will be a little lower depending on a few things, but if 80% is a good planning number, that will allow you to not run short when you need it most. We talked about capacity, and we've talked about C ratings and how that can be a little confusing where it's a discharge rate, a charge rate. The thing to understand is, and back on this slide here, I said 1C is an hour, 2C is 30 minutes, and a half C is 2 hours. That also is not true because batteries can't, the curve is not linear. If you draw, and there's a table that shows that, right? So if our 1 hour, our C1 rate is 36 amp hours for that battery, you would expect the 2 hour rate to be double that, and it is not. As you look across the chart, it's very nonlinear. We have a significant change. The heavier the current draw, the quicker we're going to deplete our battery. So there is the capacity within the battery is very, very dependent on the load and somewhat dependent on the temperature. So it is not a linear number. So we've talked a little bit here on capacity and state of charge and things like that. Why do we care? In the ham radio hobby, when do we use batteries like this? We use them for field day. We use them for Aries deployments. We use them when we support our local club at an event that they're doing in the park. We use it in our soda hikes. We use it, there's a lot of times that we use these. So the reason it's important to know is we need to calculate how much capacity we have so that when we're out using the battery, we have enough energy to run what we want. So here's a very simple scenario. Say we've got a race that we're supporting for our local club with some Aries members and some club members. There's a foot race, and we're supporting them with communications. We want to know that we have enough battery to last the entire time. So we take our transmitter that we're intending to use and we measure how much current does it draw on high power. And then we measure back and measure how much does the receiver draw when the squelch is open. We don't really care about when it's closed. It's going to be different. It could be significantly different. It could be less. But to be on the safe side, we're going to use unsquelched or open audio. Now, if I'm just an aid station supplying water out on the course, an 80-20 number is a pretty good number. We're going to be transmitting only 20% of the time, and our receiver is going to be active 80% of the time. But if we're the net control or a heavy relay station that's getting information back and forth, it might be a little closer to 50-50. These are good planning numbers. So as we move forward into that, if your transmitter draws 12 amps on transmit, 1 amp on receive, and you are not the example net control station, we just have to multiply all those numbers out by our time. We take 12 amps times 12 minutes, which is 20% of an hour, and 1 amp for the remaining 48 minutes, which is 80% of that hour. We come up with 192 amp hours, or 192 amp minutes, or divide that out, we get 3.2 amp hours. So there's a number we can do, but we have to consider that the battery's not going to deliver 100% of what we said it was going to because of Puchert's law, temperature constants, things like that. So we use 80% of the 80% of that, 30.7 amp hours to run the battery. I'm sorry, we use 80% of the capacity, so that's 30.7 amp hour battery. I recommend calculating everything in the worst case scenario, high power everywhere. You never know if you're going to need it when you're out and about, if you carry enough battery. Of course, that is going to change a little bit if you have a long hike ahead of you to get the batteries out. That will change that a little bit. All right, so we're going to move forward with charging. I've lost my presentation here. Is it still? I'm trying to figure out how to get to it. One moment here, folks. We'll get our presentation back on the screen so that we can see some of the, there we go, thank you. All right, so we're going to talk about charging these batteries now. There's so many types of battery chargers out there, it's absolutely unreal. And what makes things a little bit worse is that they use terminology that's not always correct. As far as, we print the word automatic on there. Bulk charger, okay, this is a typical charger. It might even have a float, and they'll stamp automatic on it. This is one of those types of chargers. We've all seen them. You can buy them at just about anywhere, the Tractor Supply, the big department store, things like that. This is a linear charger that puts out lots of current. It has an automatic to it. It is not smart, regardless of the word that says automatic. It's going to take the battery to a certain level, and then it's going to trickle charge it. Now, a 3-state charger, and sometimes you'll see 4-state chargers. These are what I would consider a smart charger. These are the chargers that will actually charge your battery the way you want it to be charged, and they're very safe for the battery. They have a lot of things placed in them. Some of those. This is a fairly high-end smart charger. This one is made by NOCO. This charger will actually analyze the battery a little bit before it applies what it's going to do. So this battery charger is, it has everything that other one does, but it'll do multiple different battery voltages. It's got a setting on it specific for absorbed glass mat. It's also got a setting for cold temperatures.
approximate of Puchert's law. Deep cycle lead acid batteries only give 50% of their capacity. Do we need to double our 80% number?
That is correct. You want to consider 80% of your 50% of total capacity if you want to be as safe as possible. You can get away with slipping that a little bit, but that is a good observation, and I failed to mention that, yes, if you have a 10 amp hour battery, you want to consider with Puchert's constant in there, that battery is actually only an 8 amp hour battery. Taking that down to 50% is only a 4 amp hour capacity. So good point, and yes, that is right. I've lost this screen entirely now. Oh, sorry folks, we have a Java problem, and it's not even, there we go, it's the coffee kind. Okay, bring my presentation back. Thank you. Sorry folks, it looks like we had a coffee and computer encounter here. Well, as he's working on that, the other type of charger, if you will, that you'll run across, and it may be an independent device. It also could be built into another device, and it's called a desulfator. So in the beginning of the presentation, we talked about the lead sulfate building up on the plates and becoming harder and harder to remove and killing your battery. This no-co charger actually has a repair function, as you can see here, and that's exactly what that is. That is a desulfator. There is a special mode in some of these chargers, or you can buy a dedicated desulfator, and it will help us try to remove some of those some of that sulfate that's built up on the plates. It is not an end-all solution, but it can help if it's lightly. All right, so I still don't have a presentation here.
Well, we have to actually share the presentation.
Thank you very much. Okay, so three-state charging. I talked about that being the smart mode of charging. This is something that you want to look for when you're dealing with lead-acid batteries of any kind, gel, AGM, flooded. We want a smart charger, a three-state charger. And those are the key words, because you'll find a lot of chargers out there that say they're smart, but three-state are the key words when we're looking for that. Here are the three states. The bulk charge. This is a this section of the charger is going to bring the battery up with a heavy current. It's going to come up to about 80% of the capacity of the battery. And a charger like I showed you earlier, the linear smart charge, or automatic chargers are going to deliver that energy. And then as soon as they hit 80%, they're going to go into a float charge that doesn't, it's just a prefixed, it might just be a small, maybe 10, 100 milliamp, 100 milliamp, 120 milliamp, and it just lets there, and that will actually usually cook the battery if it's left on long enough. So those are not all that automatic. Highly recommend that you use a charger like that if you need to get a lot of energy into the battery quickly, but you're going to be monitoring it and you need to reuse it quick. That's about the only time I'd recommend using a charger like that. Because states 2 and 3 are the important part to the battery health. So the absorption charge, and remember that as the battery is, if we charge our battery to 80%, we haven't removed all of the sulfate from the plates. So that sulfate, is going to, over time, build and build and build and become more and more inhibitive of the battery operating properly. So it's really important to get these up from the 80 to the 100%, and that's what the absorption charge does. Charges that last percent, and then a float or a maintenance charge keeps it at 100%. So let's go through those steps. The charging. The absorption charge, the bulk charge, this is a constant current charge, and we're measuring the terminal voltage of the battery to determine where we are at capacity. I did mention earlier that capacity should be measured with no load on the battery. However, charging is a little different story. When we're in the bulk charge mode, we can actually use terminal voltage to determine if we're above or below 80% of capacity. Now, a real smart charger, one that's got a microprocessor in it that can analyze the battery, like that NOCO charger I showed, will actually be able to look and say, oh, this is a lead acid battery, a 12-volt battery, but it's been deeply, deeply discharged. So I'm going to add a very small current to make sure that there's no cell reversal and things like that to bring it back up into a little bit of a safe range. Then it'll dump the bulk current in and bring it up to the 80%. And I should mention that although that NOCO charger has desulfator and everything else, they make all kinds of less expensive versions. This is a little 2 amp charger by NOCO. It does not have a desulfator, and it does not have all of, no jump charge, anything like this. Is a fantastic charger for Aries and, ham radio batteries. It still has all the smarts. It's temperature compensated, and it'll do the 3-state charging and adjust things as necessary.
Is there any concern leaving that on our batteries all the time?
No. So we're going to touch on a few brands. And this type of the NOCOs, there's some N-Powers. I'm going to run over a couple of them. There is absolutely no concern. As a matter of fact, it's recommended to. Battery tender is one of the most common ones that we find sold all over the place in the stores here. Those chargers are designed to be kept on the battery all the time, and they should be. So they are very safe to do. Personally, if I'm going to leave a charger on a battery all the time, which I do, I choose low charge level chargers. So the battery tenders are, I think, some of them are 1.25 amps, some are 2 amp. And I just let it charge. It's fine. It takes a long time to charge a big battery at just a 2 amp charge, but it's safe. Okay, so we're in the bulk charge. Charger watches the terminal voltage, determines the level of charge. When we hit about 80%, we switch to absorption charge. Now this is where things change drastically. This is a much slower rate of charge than bulk, and it is constant voltage, not constant current. So now we put a much, much higher voltage, source voltage, across the battery from our charger, and we monitor the amount of current the battery takes in. So a 12-volt charger, you might see it charge at 13, maybe 14 volts, but when it gets up to that 80%, we switch, the charger might go 15, 17, 18 volts, holding the voltage constant and measuring the influx of current. And when the battery absolutely stops taking any charge, we're at 100%, and it flips over to maintenance, and it just feeds the battery only what it takes to need, only what it needs. And it adjusts that day and night and temperature. It's temperature compensated. The battery will need different amounts of current to stay charged depending on the outside temperature. These chargers know that, and they do this. The maintenance charge is the same kind of, it's a current limited charge now. So after we bring the battery all the way to full charge, we put a very small, it's usually 10% or less of the bulk capability current of the charger, and that is the thing that delivers just that little bit to keep the battery up, as so self-discharge and leakage and temperature changes that naturally bleed our charge off. This is a key here. The charger has to be able to deliver 0 amps of current. As the battery temperature changes, the battery can actually reach a slightly overcharged state, and it will bleed itself back off, but the charger has got to not put energy into the battery during that time. As we mentioned here, batteries and capacities, all this changes with temperature, and all these good chargers will compensate. Now we're going to get into some of these chargers a little bit later in the lithium section, but some of the chargers like this one, which is an RC model charger, this one is made by High Tech. This battery charger, or this one, is another RC model charger made by Sky RC. These chargers, which are designed with all the features for lithium battery charging, and we'll cover that in part 2 here after the break. These chargers have, almost all of these type of chargers do have PB or lead charging capabilities, and most of these chargers will go up to 30, 40 some volt batteries if you have big lead acid batteries. So there are, you know, it's great to own a charger that's specific for every single thing, but it's not practical to do that at all times. So you can use chargers that were built for other technologies if they've got a lead acid setting. So let's talk a little bit about desulfation. I mentioned that was an option on some of these chargers. And so if the battery's let sitting low state of charge, that sulfate's built up on the plates, and as I mentioned, the longer it's sitting there, the harder it's getting and the more insulative it becomes. So a desulfating charger will either pulse DC or output a low AC current, which normally AC into a battery is a very, very bad idea. But what that does is it actually causes the pulses or the AC, it actually causes micro vibrations within the plates. So they will actually, you know, vibrate at the frequency of the pulses, and that helps to physically knock off some of the sulfate on those plates. We want to knock that sulfate off and let it fall to the bottom. And if it's not too thick, the little particles that fall off and recombine.
There's a question here from Chris AE5IT. If I have more batteries than I have good chargers, can multiple batteries be paralleled on a single charger for convenient long-term storage?
So that's a tricky question to answer. And so I'm going to answer it with some caveats. The answer is yes. You can parallel the batteries and charge. However, you would be very, very smart to make sure that the batteries are of similar state of charge when you first put them together. And realize it needs to be monitored, because if say you have two batteries at 30% of charge, and you know they're close, so you parallel them and you hook the charger up and you bring them up to 80%. I would recommend from the 80% to the finished charge that you separate them and do the last little bit of charge independently, because no two batteries are going to be exactly the same. Are you going to just destroy it if you leave it all the way through there? No, you'll be fine. But you know, I'm a big fan of batteries are very expensive, so try to get the most you can out of it. Just charge each one independently. If their state of charge is similar, you can parallel them and bring them together. When we get to the lithium battery section of this conversation, after the break, I'm going to have a different story for you. But lead acid, yeah, it's not going to hurt anything. Now, of course, if you've got an 80% charge and a 20% charge, when you hook those two batteries together, the 80% is going to heavily discharge into the 20%, regardless of what the charger is doing, and is probably going to become very dangerous and reduce the life of everything, your batteries and your charger. Now, the last thing on the desulfation point here, physically shaking the battery. If you've ever seen anyone pick a car battery up and swirl it, or they just hold it about an inch above the ground and just tap it on the ground, that's exactly what they're doing. They're trying to break off some of the sulfate and get a little more life out of that battery. Some of the smart chargers, like the NOCOs, they'll actually measure the internal impedance of the battery. They'll measure a couple other things besides voltage and determine whether or not maybe just a little desulfate here and there will help the battery stay healthy, and they'll do that automatically. The best answer here, don't let your batteries sulfate. Just put them on a good quality charger and leave them on there, and charge them as quickly as as practical after you've used the battery. Okay, someone asked earlier about the chargers. Here's a list of chargers. These are chargers I own and have experience with. There is a company called A&A Engineering. It was a single person. If you search for it, there are two AA Engineerings. One of them is an actual engineering firm, but you'll find A&A Engineering. His batteries chargers and all he's got some GPS devices and things like that. His design is, he's out of business as far as selling it, but all his schematics, all his data, everything is on the website. And these are very, very simple, low part count chargers. You can build your own. If you don't want to go buy a $180 charger or even an $80 charger, you know, that to maintain these batteries, you can, for $20 in parts and a perf board, you can build the ANA engineering design. It does use the Unitrode UC2906. That is a special IC that is sole purpose is a complete 3-state temperature compensated smart charging IC chip. All in a chip. You just put the supporting electronics, which are the power transistors to drive the current and a couple of little filter pieces, a pot for adjusting the current, things like that. And it's got some LED outputs to show you what state it's in. Fantastic design. Been around for a really long time, easy to build, and all the parts are available. Unfortunately, the kits are not, but us being innovative hams should be able to get to that real quick. N-Power is a brand sold by Northern Tool. NOCO is sold by all kinds of places. Optima, the battery manufacturer, sells chargers specifically for their batteries, but they're really, really good chargers. Battery Minder and Battery Tender. Battery Tenders are these. Probably seen that logo. It's a pretty famous logo. They make all kinds of different systems. That's an 1.25 amp smart charger, 3-stage, temperature compensated. They make these in every kind. This is a single one. They make little wall wart ones for or motorcycle type batteries, or they make 4-bank chargers. They also make 8 and 16 bank chargers, although the price goes up exponentially after the 4-bank. Here's a couple that I built out of the ANA engineering design. These are switchable, either 1 amp or 2 amp. And there's just a little ammeter on the front. That's all I've got, and then 3 LEDs to show what state they're in. Thinking back about it, I'm not sure why I chose red as the fully charged and floating LED color, but that's what I did. Okay, and then we talked a little bit about the NOCOs. Those chargers are really ahead of their time in technology. They come at a fairly premium price, but boy, here's the thing. If you think about it, if you go to the store and buy a lead-acid battery, you almost can't buy a battery for under $100, no matter what the capacity is. If that $100 battery lasts you 1 year because you're either not charging it properly or charging it with a very poor charger, the $100 a year can add up fast, and a $100 charger might make that same battery last 7 years. So it's really worth the expense of the charger up front to protect your cells. Okay, so we're going to summarize here a little bit on the lead acid thing before we take a short break. Keep your chargers on the smart 3-stage. So, to re-answer the same question earlier, yes, leave them on these chargers all the time. I have a wire rack in the garage that's full of all of my batteries. Everything from small ones on top to the big flooded lead acids on the bottom that I use for winches and things like that, and all of them sit on ANA or NOCO or battery tender chargers 24/7, 365. But here's key 2. Use them once in a while. We're going to talk about the number of charge-discharge cycles that are available in a battery. Lead-acid batteries are really, really good. You really don't have to worry about wearing the battery by charging and discharging. Use the thing. If it's possible, load test it. I've went a little overboard with some of this while I was learning and trying to figure out, what was killing my batteries. So I did pick up quite a few toys and tools to learn about this. Load testing, okay? So this little device right here is just a phenomenal device. It's West Mountain Radio, and it's the CBA4, the Computer computerized battery analyzer. And it's got, you see the LEDs, a power pole on that side, and it's got a USB on this side that you plug into your PC for the software. And this alone is, and I can't remember, I want to say this is 100 watts, I think. They ask a kind of a ridiculous amount for what they call amplifiers, which are additional loads to go above that. But I have found that this is plenty on its own to test every battery I own that I use for ham radio. And this, with the software, and these, I can't remember the price, but these are actually not terribly expensive. They will give you an immense amount of data about your battery, and you can do load tests with these, and it'll calculate your amp hours, it'll calculate everything out with all customizable settings. You can decide how much current. There's an additional license you can buy for this, which I've bought, that allows you to do cycle testing. So you want to test, remember we talked about that, your battery's running your station for your event. Yes?
There's a question here from Willem. Is the Samlex 1223 BBM a 3-state charger?
So you're making me dig deep in my memory for that particular model, Willem, but almost all of the Samlex chargers are 3-state, so I would venture a guess that the answer is yes. Can verify that after the fact, but I believe it is. Almost all of those Samlex ones are 3-state smart. We were talking about that discharge model when you're on, on the mountain at the trailhead with your radio, and I'm receiving 80% of the time, transmitting 20% of the time. I can actually use this and hook up in my software and say, I want to discharge this battery until the terminal voltage reaches, X, Y, Z. So I know that how much, slightly above dead. And I can say, cycle it. So it'll draw 20 amps for 2 minutes, and then it'll draw 800 milliamps for 8 minutes. And it'll just do that back and forth and show you that cyclic rate and show you your capacity. Now, if you really want to go overboard, West Mountain adds this device, which is a battery charge module. So I can hook the battery to this, hook a charger to the charge port, and then from the output of this, I hook it to with a Y cable. You hook this to the charger, and you hook your CBA up. And this also has a USB device that you hook to the computer. Now I can build a complete profile that discharges my battery 80-20, 80-20, 80-20, measures its capacity, then it disconnects this and it connects my charger and brings it all the way back to 100%. If you really want to life test your battery, you can do that over and over and over, and it'll show you, how, it'll do it as many cycles as you want. One is usually adequate for me. There's also some great little tools you can use. You don't need really expensive stuff to do this. This is another item sold in the hobby market, and it's a little battery analyzer. And you can hook up a battery to this, and I don't have anything to hook to the drain side, but you can see on the screen, this is showing me current being drawn, which there's none right now, current of voltage of the battery, the number of watts, and it'll cycle through, and this will actually show you amp hours consumed. So you can actually leave this on and use this as your measurement of amp hours if you don't want to buy a computer analyzer. It's just a little more manual labor to keep everything safe.
I see that there's a marking on the front of that says 130 amps. Can I use that at 130 amps? Briefly.
It actually, I've opened these up to see what's in them. The reason it says 130 amps is there's actually a shunt right here in the back, and that's how it measures the current, is the voltage developed across the resistive shunt, which is like a hundredth of an ohm or something like that. The device probably will withstand 130 amps. However, 14 gauge wire that they have on the ends that this comes with probably won't stand 130 amps very long. So technically, yeah, you can use it. However, I think that's a little bit of an exaggerated rating there. I also mentioned in the presentation, if you don't have a good load and you want to test your battery, you can use that simple little gauge there, which I think those are about 9 or 15. They're less than $20.
I bought it for $18.99.
Yeah, so less than $20 for that little Turnigy battery analyzer. And then for a load, use a car headlight, one of the old incandescent sealed beam. Yeah, the nowadays LED and halogen are popular, or HID. Use just an old standard incandescent headlight will provide a great load for you to test a big battery. Okay, so wrapping up here with lead acid here. So taking good care of your batteries with a small investment in your charging and monitoring technology will save you big. I have a lot of piece parts here, but none of these, there's a few expensive chargers, but all the rest of these little gizmos and things, they're all fairly inexpensive. A car headlight you can buy for probably $10 if you go buy some, just small El Cheapo one. The little analyzer there is $20. Yeah, you'll have to watch it and cut it off when it reaches the right voltage, but you can accomplish the same thing as the computerized one does unattended. And then, of course, just remember, batteries are heavy and they're full of acid, whether that acid be liquid or absorbed in a mat or gel, but it's acid nonetheless. So just use some caution with that. And that kind of wraps up where I am for lead acid. When we come back, we're going to address lithium batteries, and they're a whole new world of pros and cons and safety issues and everything else imaginable with lithium, but we're going to go over all of that after the break.
Okay, everybody, we are going to go into a 15-minute break.
Welcome back, everybody. If you just joined us over break, I'm James, KI0KN, and first half of this presentation we talked about mostly lead acid batteries. We're going to go ahead and talk about lithium chemistries and all of the differences and specialties that set them apart from lead acid, and what some of the pros and cons are. So lithium's a whole new world, and it also comes with a whole new set of pros and cons. Disclaimer here. In this section, we are going to talk about safety a lot. Certainly you would think a 50-pound battery full of acid is something that we'd emphasize safety on. Lithium is just shoots it out of the water for safety. So, okay, if you still need to grab a cup of coffee and you don't want to hear any science, the next 4 slides are for you. All right, lithium ion, and I'm gonna read some of this as it's pretty small. I hope it should be okay on the screen. Lithium ions are involved in the reactions driving this battery. Both electrodes in the lithium ion cell are made of materials which can intercalate, which is a fancy word for absorb, lithium. Intercalation is when charged ions of an element can be held inside of the structure of the host material without significantly disturbing it. So already you'll hear some differences between this and the lead acid and how the structures in the molecules in the battery are interacting with the physical structures in the battery. In the case of lithium ion, the lithium ions are tied to an electron within the structure of the anode. When the battery discharges, the intercalated lithium ions are released from the anode, travel through the electrolyte solution, and are absorbed or intercalated in the cathode. So this is talking a little bit about our charge and discharge process. So as the battery's charged, an oxidation reaction occurs at the cathode, meaning that it loses some negatively charged electrons. And to maintain that charge, because everything always has to be balanced, an equal number of some of the positively charged intercalated lithium ions are dissolved into the electrolyte solution. These travel over to the anode, where they are intercalated within the graphite. The intercalation reaction also deposits electrons into the graphite anode to tie up the lithium ion. We're almost through all the super technical type. During discharge, the opposite happens, right? So the lithium ions are de-intercalated from the anode and they travel back through the electrolyte to the cathode. And this also releases the electrons that were tying them to the anode. And these flow through the wire, providing power to our load. The current that we have, the current flowing through to do work. And it's the connection of the external wire that enables the reaction to proceed, just like lead acid. When the electrons are free to travel, so are the positively charged lithium ions that will balance the movement of the negative charge. And last wordy slide here, I believe. Second. Transfer of lithium ions from the electrodes occurs at a much higher voltage than in other battery types, so they must be balanced by an equal amount of electrons. A single lithium ion cell can produce a voltage of 3.6 volts or higher. Remember, we talked about 2 volts for a lead acid battery. So these are significantly higher. And you know, your alkaline type batteries are usually around 1.5 volts. A couple of basics for our ion. Instead of lead anodes and cathodes, they're usually graphite in a lithium battery. However, repeated insertion of lithium ions into the standard graphite structure in a typical lithium battery eventually breaks apart the graphite. So I mentioned in part 1 that lead acid batteries were nowhere near as sensitive to the number of charges and discharges as lithium batteries are. That is why there's really no destructive force that happens in the charging and discharging of a lead acid battery other than the sulfate buildup. So we are actually having physical destruction happen within the battery at a very, very slow rate, but it limits the charge and discharge numbers greatly. And to give you an example, a typical lead acid battery might go 2,500 or 3,000 discharge cycles. A lithium ion is more along the lines of about 200 to 300 cycles. Now, first thing you're going to ask me is, well, I charge my laptop up and down every day and it lasts years. It's true. And a little bit of that is because we're going to get into some of the other types of lithium chemistries, and your battery may not be just a simple LiPo battery in there. Okay, so we're going to move to variants. Lithium, we call everything a lithium ion, or we call it a LiPo. Well, lithium ion is a correct term for all of the types because it is the lithium ions that cause this reaction to happen. However, LiPo is one specific type of lithium ion battery. Lithium polymer, very typical in RC. All of these batteries here that you see, these are lithium polymer batteries. More typically, they are just a shrink-wrapped set of cells. We're going to look at the inside structure of these batteries here in a little bit, but those are what's referred to as LiPo or lithium polymer batteries. The next one, lithium iron phosphate. Lithium iron phosphate batteries, more typically referred to as LiFePO. We don't mention the 4 in there, just call it LiFePO. They usually are capable of a higher discharge rate, and because they're capable of higher temperature coefficients, they are much more tolerant to high temperatures. That makes them a safer battery, and they usually last longer. However, they also self-discharge faster than a LiPo battery does. So everything has its pros and cons. There's always a caveat to everything. Now the next one, you hear not as much about this. Lithium manganese oxide, lots of laptop batteries are of this variant. This battery is safer yet than LiPos and LiFePos, but it's got It's got a lower capacity. My slide says shorter overall lifetime, and that is true if you cycle the battery heavily a lot. But in the case of, for example, our laptops and things like that, we often don't cycle those all the way down to dead. So that, sometimes yes, sometimes no, sometimes we keep them. They tend to have a longer life. And then the last one, and by the way, these 4 listed are not the only 4 types of batteries out there. They're just the 4 that we run into the most in general everyday occurrences. The last one is lithium, nickel, manganese, cobalt, oxide. And that, I don't even know if there is a, NMC, I guess, is what we call that one. That's a mouthful of letters, but nickel really significantly changes the game in the lithium world. Where almost everything is better. We get higher current, longer life, longer overall capacity. They are still very safe batteries as far as on the safety scale goes. And these are the ones that you'll find usually in EV cars. Most of the electric vehicles are these NMC type of batteries. So we talked about lithium. It's much higher energy density. We've got higher voltages because of the reaction. And by the way, one of the differences, why do we have that higher energy density? We didn't get into this in the chemistry, but what causes the higher energy available out of the same size or smaller cell. In a lead acid battery, our molecules have to actually travel, and our electrons, ions, whatever the case may be for each battery type, have to leave one of the electrodes, travel through the electrolyte, and attach to the other electrode. And there are those molecules, as they're coming across, those particles, they have to leave here and attach there in a lead acid battery. That's not true in lithium. In lithium, in the electrolyte, we have many particles. That particle can attach, and we're kicking electrons on and off, and that can exchange all the way across the electrolyte. Because of all of those free particles in the electrolyte, we can make that transfer from one to the other extremely fast and in massive parallel, because there are so many free particles in the electrolyte that allow that chain reaction to happen at many, many times the speed it can in a lead acid battery. So that's actually what gives us the density and the high discharge rates in lithium batteries. All right, so we go back to our slide here. Because of the higher energy density, the batteries are smaller, they're lighter. We can discharge them at far, far higher rates safely than we can lead acid. Many people that have come from the nickel metal hydride or NiCad days remember memory. You had to actually discharge your battery all the way flat every once in a while, or it would develop a memory that would, if you only used 20%, eventually the battery became dead at 20% usage. So this sounds like an awesome technology. We're ahead in every way. What's the catch? They are far, far more dangerous batteries. This picture was sent to us by a local Colorado ham in the area and encouraged to use it as a public safety slide. This was a lithium polymer, a LiPo battery for his drone that was sitting on the desk, and at 4 a.m., no warning, no reason, it exploded, caught on fire, and caused a significant amount of damage to his ham shack, as you can see there. This is not an atypical problem for lithium, especially LiPos, but they're all capable of it. It's just that the LiPos are the most likely to do this. They like to shoot fire and poisonous gas and high pressure gas. They are very, very dangerous. What are some of the other cons of the battery besides just the safety? If you're doing it right and you're taking the proper procedures, which you should with all lithium chemistries, when you're charging, discharging or storing the battery, you should be doing so in a safe, contained manner. We're going to get into that. They are shorter life. As I said, a couple of 200-300 cycles, full cycles on a lithium battery. They're getting better, but that they are farly greater limited. They are greatly further limited than lead acid batteries. The other thing, because of that graphite destruction that we talked about earlier, lithium batteries stored at 100 or near 100% charge will essentially eat themselves. That graphite is being destroyed at all times that those ions are intercalated in the graphite. So if you store them at high storage volumes, storage capacities, the batteries will go bad much, much faster, not using them at all. So we must store them at a reduced storage capacity in order to get the most life we can out of our lithium packs. More cons. We have to charge them with special chargers. If we hook up one of these lead acid chargers to a lithium pack, that alone can cause the battery to explode or catch on fire. It's not a guarantee, but there's a far, far greater chance. And then the last thing, and this all comes down to this energy density problem, or this energy density issue, we have to balance the cells in our packs to maintain safety. If a cell goes bad,
there's a question on the chat here is, what is the most typical chemistry in smartphones?
so it's either going to be a pure LiPo, and I'm going to talk about why they can use those more safe than everything I just talked about. Or the second very common one is was the third bullet, the nickel. I can't remember here we go. The lithium manganese oxide. One of those two. It's either a LiPo or a lithium manganese oxide are the most common cell phone batteries. Also with laptop batteries, that's true. So those are the most typical chemistries that we see in our everyday electronics. Okay. Now, let's look at the differences about this. On the left, you see a lead acid battery. That is each one of those cells, right? Those are the 2-volt cells. This is a SLA or slab, sealed lead acid battery. The electrolyte is infused in those fiberglass mats. And then the cells are interconnected, and then on the end, one of the electrodes is brought up to the top for plus, and on the other side, the minus. On the right side, we see the lithium chemistry. And the lithium chemistries are typically built, each cell is a small polymer bag squirted with the electrolyte inside of it, and then the electrodes at the end. And they are often like little pillows that are sandwiched and folded back and forth. And then there's typically 3 case types. These batteries, as we showed here, this is the one you're looking at or you were just looking at on the screen, is this type. If you look in the end, you'll see under the packing tape, those are just the little sacks full of the lithium and the electrodes, and they're all folded over back and forth on each side. And then on the other end of the battery, where the folds come together, we have our wires coming out. And then there is simply just shrink tubing over that whole pack. So that's one of the typical casings of the battery. Now, this is the same battery, same type of battery, but you can see this is in a hard plastic case. So this one's a little more safety, a little more safety conscious. Both of these are kind of intended as radio control model batteries. So there's one obvious reason to use the other battery over this in your model airplane, and that's weight. So these are a little bit safer. They're certainly more puncture proof and contained if they do blow up. But they're certainly much heavier. So that's why the construction. Now the third and last construction is, when you look at a pack like this, it might look like like a NiCad or a NIM pack or alkaline. Same deal, but they're inside of the traditional metal case that we find in older technologies. These are by far the safest because they have a metal case around them. And you will find that laptop batteries, cell phone batteries, all those, they have various shaped versions of these steel encased cells inside of them to make the pack. So that's another major safety factor towards those types of batteries. All right, let's go back to the presentation here and look at some pros and some cons here. These are the probably the most important ones to keep in mind as we compare the technologies. Lithium has a far higher power density. We store more energy in a smaller physical space than any of the other types. The other advantage of lithium is we can discharge them at insane amounts of just really high current rates compared to any of the others. However, the inverse does not hold true. A lead acid battery will take a heavy charge safely compared to a lithium. Lithium overcharging is a great way to catch them on fire. So you have to be very careful on the charge. Storing. You want to store lead acid batteries at or near 100% and keep them on the charger and keep them charged all the time. Lithiums, if you were to do that, will just kill the battery when it's in storage, and you don't want to do that at all. We need to keep them at less than 100% charge. We're going to reach into that a little bit when we talk about storage. And they have to be stored safely. So puncture, temperature, and short circuit prevention are critical things for lithium batteries. Short circuit prevention is critical for any battery, but short of dropping your adjustable wrench across your car terminal batteries, you're probably not going to have a catastrophic failure of a lead acid battery with those other things. You might have some acid leak or something like that, and that's not a good thing. However, it's usually less of an issue than a full-on explosion followed by fire and toxic gases that can kill you, which is very typical to come out of a lithium battery that's been punctured or has failed in some way because of a short. And storing them, when we get to storage, we'll talk about temperatures and environments that we want to store batteries in. All right, so we're going to talk about terminology because there's some common terminology and there's a little bit different that's custom to lithiums. Lead acid, as we said, the nominal voltage is 2 volts per cell. 6 cells in series gives us a 12-volt battery, which is typical. The nickel-based batteries, the NiCad and NIM, nickel metal hydride, are usually 1.25 volts per battery, giving us, a 4-cell pack in series is about 5 volts. Alkalines are 1.5, so it's about a 6-volt pack. But lithium chemistries are advertised typically very differently than lead acid or any of the other types. We're so used to seeing volts, right? This is a 12-volt battery. This is a 3-volt battery, a 1.5-volt battery, or cell, whatever you want to call it. LiPos usually list their, they will often have voltage on them, but they use the terminology S for the number of cells. And as a side note here, I tried to research prior to this presentation what S meant. And I could find no indication anywhere on what it truly meant. The best I can tell, it means series, the number of series connected cells. But, maybe someone in the industry or something may have a better answer for that, but I do not know, other than series, what S might stand for. The nominal voltage of these, as we said, is significantly higher. 3.7 volts for a LiPo or 3.3 volts for a LiFePO cell. So you can see our nominal voltage, right, on a 4-cell LiPo pack is 14.8 volts, or for Life is a 13.2. Now the construction of these put together, you may see folks, manufacturers advertise not only S, but P. So an S designator and a P designator. This is what they mean. A 4S, 1P are 4 series connected cells. 1P would be parallel, one set. Whereas a 4S, 2P is 2 4S batteries that are paralleled together and then connected out there. So what does that give us? Double the current. Same voltage pack, double the current availability. So you'll sometimes see the P designator on the packs. Okay, we're going to talk about the nominal trap. We all know that when we talk about a 12-volt battery, car batteries or our AGMs that we use, we can hook those up to a device that expects 13.8 volts. We see that number 13.8 volts, right? LiPos, because they have a 3.7 volt nominal voltage, 4 cells at 3.7 volts, 14.8. That's getting a little bit high, but if you plugged most amateur electronics in, the 12-volt electronics, they're going to be fine with that. I think you'll find 15 volts is a very common max voltage for 12 volt or 13.8 volt things. All right, let's look at why nominal is a trap. Nominal is a class of voltage in lithium chemistries. It is not the actual, it's not really any voltage at which the battery is. Fully charged batteries, a fully charged LiPo is 4.3 volts per cell. 3.7 is nominal, 4.3 is fully charged. Look at that total voltage for a 4-cell pack, 17.2 volts. That will do damage to an awful lot of our electronics if you plugged the battery into a 4S. Sounds great that you can have a 5 amp hour battery in the palm of your hands, but we can't do it here. And so yeah, cut down to three cells. Well, 12.9, that's going to run it, right? But if it's a 23 amp 100 watt transmitter, you're probably already less than 100 watts out at the 12.9. And remember, that's the high voltage. It's going to start falling immediately. So LiPo is not a great chemistry for us in our amateur radio for 13.8 volt. So what's a more friendly solution? Well, remember the LiPos were 3.3 volt cells. They're about 3.6 volts when they're fully charged. So look where that puts us. That puts us at 14.4. Now an empty battery is going to be a little closer to that 12 range, but that still puts us right into our operating range. So you can safely hook a device intended for 13.8 volts, like most of our transceivers, directly into a 4-cell pack. As a matter of fact, although I don't get to do it very often, one of my favorite parts of ham radios is SOTA, or Summits on the Air, where we hike to the top of the mountain with an HF transceiver and activate. These are the batteries that I build and use for my SOTA adventures. These are 4-cell or 4S 1P LiPo batteries. That little pack right there is a 1.5 amp hour pack, and you can see the size of it. Those are 18650 style cells, and it's it's very light and very small. And this little 4-cell pack gives me 40 minutes on a Summit running even full CW at 10 watts, no problem. That battery essentially replaced what I had to take before this one. This is a 7 amp hour, which is certainly more than I need, but this thing probably weighs 15 pounds compared to about 1. So there's a very good power density demonstration, and why LiPos are a little more friendly. Remember also that LiPo, because of its higher temperature coefficients, is also a safer battery for us to use. So, ever wonder where that 13.8 volt number came from? 12 volt battery is a nominal 12 volt battery, but a real life, each of those 2 volt cells is 2.3 volts fully charged in a lead acid battery. times 6 cells in parallel, in series, 13.8 volts. So that's where that number comes from. All right, let's talk about charging lithium batteries. We mentioned that you need special chargers, with one small caveat we'll mention here in a while that is exclusively true. It is exceptionally dangerous to charge lithium batteries without a charger designed for lithium batteries. The good news is that because lithium is so prevalent in the radio control model industry, there are more chargers at inexpensive prices than you could ever imagine to choose from. So finding one that's affordable is very easy. There are 3 types of charge that most chargers offer, and it's fast charge. Fast charge is going to be similar to the bulk charge in the lead acid world. So it's going to give us 80% of our charge very quickly. Now, not as quickly as lead acid. We can't just dump 50 amps into a battery and bring it up fast. You can do that with a lead acid battery, and one of your biggest dangers really is only the hydrogen gas it creates. So if you can safely vent that, you can put a bulk charge in a lead acid very, very fast. Now, you can put a couple amps into your little pack and get it up to speed much quicker if you want to go fly your airplane or go run your radio a little bit more, but it still doesn't top the cell all the way off. Now, the second type of charge is normal. A normal charge does not look at the individual cell voltages, but it does look at the overall voltage, and it typically charges at 1C. So if this battery here that we were looking at earlier, this 5 amp hour battery, we would charge this battery at 5 amps. So a small pack like one of these this little zippy pack here, which is a 850, and this is a 2 cell, we would charge this at 850 milliamps to be a 1C charge. And that's the safest choice. If you can charge at 1C, that's by far the safest choice. Now, the last charge, and we talked about the importance a little bit about balance. It's called a balance charge. So it's still a normal charge. We're going to take the cells to 100%. However, as we charge and as we finish charging, we're going to measure the voltage on every single cell in that series pack and deliver either a charge or a load to each cell individually to make sure that the terminal voltage on every cell in the pack is exactly or very, very close, within typically 100th of a volt, the same. And that is by far the safest, healthiest charge you can apply to a lithium pack. Is called a balance charge. So, the importance of the balance charge. We're going to monitor the charge process from start to finish, the charger is going to, and it's going to monitor the cell voltage in every cell in that pack. What happens if we have a dead cell in a pack all of a sudden? What happens if we develop an internal short in a pack? What happens if that cell bursts? Well, if we're just putting a bulk charge in the front connector, even at a 1C charge, we're not watching each one of the cells, and something happens within the pack. Fire is a possibility. The pack could just flat out fail, and when we really need it. The other thing is, if the failure is not a catastrophic failure, it could start discharging when it sits on. You charge it all the way full, set it on the table, without knowing that one cell is either imbalanced or dead or something like that. The pack will self-discharge and not be ready to go when we need it. So, balance. How do we either add a load or a charge to every cell in the pack? Most lithium chemistries, we're going to have this connector, which is our main power connector, and then we're going to have a balance connector. And you can see this is a 4S or 4-cell battery. So we have 5 wires coming out of there. And how is that wired? We've got a diagram here on the presentation that shows the internal parts of the battery. So each one of those balance plug wires goes to the junction of a plus-minus interconnection within the battery. So if you look at that diagram, for example, and I want to know what the cell voltage is on cell 1, I can measure cell 1's voltage between pin 1 and actually what's missing in that little balance connector is the ground. You'll always have a ground wire there. No, I'm sorry, it is there. So between 1 and 2, I can measure cell 1. Now between 2 and 3, the blue and the green wire, I can actually measure the voltage of cell 2, even though it's still series connected within the pack. So this is how the balance charger, some add a small load to discharge the cell ever so slightly, while the others are charging. Some charge the cells independently until they are usually within 1/100th of a volt. And this brings not only the ability to bring the pack up and the cells to be equal in every way, but it allows the charger to detect if one of the cells has an anomaly. If one of our cells is, falls outside the parameters and the charger can't charge or discharge it properly, or, can't bring it within, it can say, hey, we got a bad pack here. We should probably stop, and you should probably look at this. So that's a great addition. Now, balanced chargers come in all shapes and sizes. However, again, from the RC world, this charger here is a very common Sky RC charger. You'll see, here's our main port, and I use power poles on everything. And you'll see right here, these are where the different balance connectors connect. This particular charger can charge 2, 3, 4, 5, and 6 cell or S batteries. So this charger would not be capable of, well, you don't need to balance charge a single cell, and above 6, you would need a different charger, or settle for the fact that you can only normal charge and not balance charge. While we're on the topic of this particular charger, or these types, these balance chargers, I want to show a demonstration of why it's very important to set up the charger properly. In this, we have a LiPo battery selected, 4S, and we're going to charge at 3.2 amps. So that is one of these cells that I made, is a 3.2 amp hour 4S battery. The charger would be, except, do you see what's here? This is LiPo. So when we connect this up, and we connect our balance connector to the side, if I were to tell this battery to charge right now, it's checking. Yeah, so we're in a little bit of a dangerous situation here. This is a LiPo battery, but we have the charger set to LiPo. Now this battery is sitting at storage levels right now. The charger says, that's okay, I can charge this. If I were to hit charge on this right now, this charger would attempt to charge this battery as if it was a LiPo, lithium polymer. It is very possible this battery could explode or catch on fire. Even though it's steel encased cells, it would at least probably blow apart. So it is very, very critical that you set your charger up properly. So here we'll change the battery from LiPo to Life. And you'll see on these chargers, there's a lithium ion for the other chemistries. Here's a lithium HV. I'd have to look in the instructions to see which ones each one of those are. There's a nickel metal hydride, NiCad, and lead. So they're all possible, but it's super, super important when charging lithium batteries that you select the right setting from the get-go. And I've gotten into a menu here where, okay, LiPo, and so we'll change that to Life, and then hit enter. So we've got 4S life. Now when I do this, it'll check the battery again. It's all good. Now I can actually hit start, and you will see the charger terminal voltage of the battery, how much current it's putting in the battery, and then the time that it's running. That's just a count up from 0. And this is sort of their attempt at showing basically how much total energy is going into the battery. I'm not sure that that actually relates to an actual, it's a mathematical calculation based on time and amount of current, and it's not really amp hours, but it's a number you can reference to see how much energy basically you put into one battery compared to another. So this battery is charging, and you saw the current ramp very slowly from 0 up to 3.2, which is a 1C charge on this battery. Lithium chargers tend to be very, very gentle on the batteries. So this has a soft start charger, and you'll see as it hits stage 2, we'll watch this terminal voltage jump up probably to 14.8, 14.9 volts, and then we'll start to see the amps decrease as it starts towards the trickle. This charger will finish, and it will beep at me and tell me it's okay, that it's done. Very important that you set those right. All the chargers have them. Here's another charger, and you'll see it's a totally different menu layout, but all of the selections are about the same. Number of cells, the chemistry, the type of charge. This one has an external balance board for the different cells. This one is also a 2 to 6 cell, and then your main terminal there. So be very, very careful. If you notice this, I'm charging a lithium, a LiFePO battery here. I'm going to stop this and disconnect my battery. I'm going to power cycle my charger. When I plug it back in, look where it defaults. LiPo. Does not. Most of these chargers do not remember where you used them last. So check that every single time. Very critical. Do that and you'll be safe. So, I mentioned that you can't use a regular charger with a lithium pack. There are exceptions, just like everything in. Some cells are built with these little guys on the top of the cell. Now this is a very small one for a small, like either 18650 or 26650 type cell like we looked at in my pack here. Basically the smarts that would be in the charger to monitor each one of the cells is built in this tiny circuit board that sits right on the top of one of the electrodes of the cell. If every cell in the pack has this, these will protect the cells from over and under charge. So we don't technically need a balance charger. However, the charger still, if the charger is just providing current and has no way to monitor each of the cells, yes, this is a fire and damage prevention method, but it still isn't as good as the balance charger for these smaller packs. You're going to find these types of things usually on larger cells, like this one. This is a Battery Tender brand smart lithium battery, engine starting battery for motorcycles and that type of thing. This is a battery that's rated at 2.5 amp hours, but it's a 150 amp cranking battery. So there is not a lot of total energy in this battery, but the energy that is in the battery can be released very, very fast to start an engine. Anybody that's seen a motorcycle battery, they're a little bit, they're somewhere between the size of the 8 amp hour and the 18 amp hour lead acids, but they're heavy. They're full of acid. They weigh probably 5-10 pounds. This little Battery Tender lithium battery weighs 14 ounces. So it's a huge savings. That Battery Tender in that case, as it was on the screen there, those cells all have those little cell protectors on them And this can be charged with a typical 12-volt lead acid type charger.
Why is there two set of terminals?
We'll have to ask battery tender that. There is no chemistry reason for that. It's probably an application reason. So, okay. So let's see. Did I mention safety anywhere along this presentation? These things it's so easy to become careless or complacent with these types of batteries. They have to be treated carefully during charge, storage, and discharge, and they can fail at any time. Remember this slide? This happened to our fellow ham at 4 a.m. just sitting on the table. It was not doing anything. It was just sitting there, and it decided, something failed, and this thing catastrophically caught on fire. And he reminds us, and if there wasn't enough PSA in here now, this is what saved his life, his home, who knows, his home, so many things. He had a working fire extinguisher. He knew where it was, and he was able to extinguish that. It damaged his ham equipment and, of course, the battery, but nothing else. I mean, this is a great reminder that, whether you use lithium batteries or not, it's not a bad idea to have one of these nearby and make sure it's good. Now, charging safety. This is the cheapest, easiest way that you can charge, discharge, and store, if you like, your lithium battery safely in your home. These are little bags or a sack, as you saw in that picture. They're like a little lunch cooler. They're typically Kevlar reinforced and made of things that are fireproof. This case will easily contain both the explosion, the flying debris hazard, and or the fire from one of these batteries that fails, or many of them. You can fill this thing to the top with lithium batteries, and this could save property, life, you name it, right? So this is just the simplest way to store, charge, or discharge your battery. When I set this on the table, it's a little bit harder with the balance connectors being so short, but I'll set sometimes. I'll take a couple of my batteries and I'll just set it in there with the leads hanging out, and set my charger right here on a little stand. And that way, the battery, when it is being charged, is completely safe. When you're done charging it, you can just tuck those in, zip it up, and store that. And I have the wrong slide there. I have a slide deck missing, or slide missing out of this deck. I use these. This is an ammo can, a military surplus ammo can, steel construction. And the way I store my batteries, I store them like that, with the lid just cracked open, and make sure there's nothing there nearby. So that's a cheap, easy way to store my batteries. I'll get to that. I jumped the gun a little bit on storage. We're still on charging. I want to talk. There was a question in the first section about parallel charging, and I said, with lead acid you can do it a little safer. These boards, these are parallel charging boards. These boards are designed to do exactly what you asked about. I think it was Chris that asked about this. And you can see these have both paralleled bulk charge connectors and paralleled balance charge connectors. Okay, don't use these. That is asking for an absolute disaster. Do they work? Yes. If you have a healthy battery, all of your batteries that you're trying to parallel charge are very, very close, 1/10 of a volt or less in nature. to each other, you know, in comparison to each other, that will charge them with a single charger. It will even balance charge, sort of. You got to remember now, though, because now each cell is actually paralleled with the cell in its other, in all the other packs. So if any one of those cells is out, you also have a chance for fire. Those work in an absolute pinch. If you were to use a balance, a multi-charger like that, a parallel charger, you should do so in the absolute safest place possible, where multiple batteries may fail at the same time. It's if you can avoid doing it, it's just better to avoid it. In an absolute pinch, you can use that. So those are you know, available, but warned. So try not to use those. All right, so as I said, jumped the gun a little bit on storage. Let's move into storage a little bit on the batteries. Here are my ammo cans. Here's some specifics about this, because if you don't think ahead of all the possible things that might happen, you can be using a storage charge bag, you know, like this, and you might still have some problems. As you can see from my pictures here, I leave my cans on a wire shelf. So at the far right picture, you can see I'm raised from the floor. Because I store quite a bit of batteries in there, if one pack's going to go and the fire starts, it's very possible they're all going to melt down. We're going to have a heck of a thermal event inside that can. So I keep my cans raised off the floor, so the heat levels are fine there. And I keep the lid cracked, so that if there is a major fire there, the fire can escape here, and I don't build a huge pressure up inside these cans. These cans are pretty tight when they're sealed, so I give it a vent. But I make sure there's nothing above this on the shelf. So fire can come out of here, in the house even, and not catch anything else on fire. That's the goal. And then, of course, if you use something like an ammo can, you got to be a little careful of pinching wires. You know, make sure you don't pinch and short a wire as you close the lid. So the storage bag, these are, you know, I think this can says $15 surplus and hold a lot of them. This bag, I think, was $8. And, you know, you can hold not as many, but you can hold a fair bit of things in there. So we're not talking about a lot of expense to be very safe here. Let's go back to the presentation, Mark. Okay. When we store our batteries, I mentioned earlier that we need to store them not at 100% charge. The graphite will destroy itself in a fully charged battery, so we need to bring our batteries either up or down to a storage level. And there always seems to be conflicting data about this, but some manufacturers are starting to actually print specs on this. And you know, as far as how down or up, as your case may be, do you want to keep it? The only thing everyone agrees on is that it's less than 100%, but there are some fairly generally accepted standards starting to come out from many of the manufacturers, and that is 3.8 volts per cell for a LiPo pack, or 3.3 volts for a LiFePO set, which you'll notice are 1/10 of a volt higher than what they call nominal voltage. Don't ever store them at 100%, and don't ever store them dead. The other thing that's really important, unlike a lead acid battery, we want to store lithium chemistries as close to room temperature as possible. Too hot actually accelerates the graphite destruction, and the batteries will fail prematurely. Too cold is not a problem to store the battery. However, it's very dangerous to charge a lithium battery when it's cold. So that's another thing to remember. If you left your batteries in your trunk overnight in the middle of winter, you should let them warm up to room temperature in-house before you charge them. It can be a fire hazard as well to charge a cold lithium battery.
I've also noticed a couple of little weird situations. What's the deal with my cell phone dying when it's really cold?
So energy density reduces in all battery chemistries at lower temperatures. The chemical reactions are slowed, and you can't, they don't happen as quickly. The battery self-depletes in the cold, not as much as the hot, but it does self-deplete some. I wish I could give you a better, more technical answer than that, but that's about as far as I understand it. It's really based mainly on the chemical reactions are affected by the cold, and the energy density of the batteries is reduced. So, yeah, slowed significantly down.
Yeah, James, we've got a question here from Keith. What's the best or safest way to dispose of old dead LiPo batteries?
Yeah, you just chuck them out the window on the highway. No, no. Cities are becoming more and more progressive on recycling programs for these things. I know up where I live in Loveland, and Fort Collins, they have all of the transfer stations, the recycling centers, everybody, they all accept batteries. They usually just ask you to tape over the terminals.
Home Depot, Batteries Plus, they both take them.
There you go, Home Depot, Batteries Plus. There's lots of places, but there's a lot of, I don't think any batteries are really great to just throw in the trash. There's an environmental impact on all of them, but lithium has some pretty nasty chemicals in them, so recycling them at a recycling acceptor is really the best option.
Yeah, no, Dean pointed out Home Depot takes lithium. I guess that's good to know. I didn't know that.
Yeah.
Greg, K0MGL has a question. So should I keep my HT batteries at partial charge in my go bag and keep my HT on the shelf at partial charge?
So, my answer to that is no, with a qualification. It's no because a go bag's sole purpose in life is to be ready to grab and go at a moment's notice. So are you going to get, if you keep it fully charged, you're going to get a shorter battery life. There's no question about it. It's not so much of a difference that it's going to be, you're not going to go through a battery every year if you keep the batteries fully charged. I keep all of my lithium batteries for ham radio, with the exception these packs here with the LifePos and things. I do keep those at storage levels. I don't use those as go batteries. My HTs and things that I expect to be able to pick and go, a go bag, I keep them charged at 100%. It's a trade-off. You're either going to really extend the life of your battery to the absolute max, but have to charge it first, or you're going to have something ready to go at a moment's notice, which is by definition what a go bag is. So my recommendation, and at least my personal practice, is I keep batteries that need to be used at a moment's notice fully charged and accept the little bit shorter life versus
Still get 3 to 5 years out of it.
you will get 3 to 5 years out of them. And the way to maintain, if you keep them fully charged and stored, the way to get the most life out of them, twice a year, use the radio until it's nearly depleted, and then recharge it fully. That will help. That will help, help that. So you gotta, there's a balance. We'll talk about that in a minute. You've got to find a personal balance of what's acceptable to you, to do that. I personally would leave any go bag batteries, HT batteries, fully charged. It's not like you're going to get 6 months out of it if you store it full, and 5 years if it's stored half.
Cycling batteries on every use will really shorten your actual useful lifetime too.
Yeah, yeah.
Mention that.
So cycling your battery completely up and down shortens its life more than using a battery partially the way down and recharging it. Since we don't have memory problems, that's not an issue there. And so we will get, I said 250 cycles. That's like 250 from 100% full to 100% empty over and over and over again. You're going to have a significantly greater amount of real cycles there, because we don't use our batteries typically until they're dead flat.
Yeah, I had a question. I know on some of the Motorola radios I have, and they've got the Impress chargers, I don't use the radio a lot, and it seems like every time I want to put it in the charger, it wants to go discharge it and bring it back up. So do you just do it occasionally and bypass it the other times, or what are your thoughts on that?
Personally, again, I bypass it most of the time, and then about every 6 months I'll let it take the familiar orange light on the Motorola. Yes, personally I use about 6 months. I will bypass the orange light that wants to do the discharge cycle. In about every 6 months I'll let it do a full cycle on the battery. Because the Impress is a smart thing that's talking to the battery and the cells, it can learn about the conditions more. You're going to get a better life if you just sort of let the charger. Remember that those chargers, the software in those chargers was written with commercial use in mind, where it's all the time. Those batteries are being used every single day. Those chargers weren't designed to keep batteries the most healthy that we use every 2 months once. So I bypass it most of the time.
So, so if you've used your radio quite a bit, and and it hasn't been that long, and it's almost totally dead, will you let it go ahead at that point if the battery is almost discharged, or do you still pretty much stay with the 6 months?
I stay with the 6 months. I try to keep mine on a fairly regular schedule because I have so many batteries sitting there. If I did that, I'd forget when I did which ones last. I try to do them in bulk. Some weekend I'm down in the office or something like that. I'm like, this is a good weekend to just cycle all of them through, and I take them all down, all the way up over a 2-day period. And so, personally, again, and you will find as many opinions on this as you will as anything. So. When I pass my personal opinions on about these subjects, it's because I have found by trial and lots of error that they seem to last the longest with this type of.
You may want to just briefly, I don't know if this microphone's working. I thought the microphone was working, but a couple of the questions that I asked about that, maybe you want to summarize the questions. I got a comment that they couldn't hear it from us in the peanut gallery.
Okay. Can people hear? Or am I?
I think it was me. I don't know.
Oh, okay.
If somebody can type in the chat, are you hearing me now? I did switch microphones.
You can look at.
We can hear you okay, we can't get you.
Oh yeah, John doesn't have a microphone, so I'll repeat any questions, things that come up. Yeah. Okay. Thanks, Willem. All right. So let's go back to some storage safety. Here's the next one. Puffiness. So you're not going to see this in.
Talk about that with your wife.
Yeah. I've got a peanut gallery here too. But the steel canned cells or the hard packed cells, you're not going to see this. But in these, or at least probably not going to see this in these cells like this that we were referring to earlier, where they're the shrink wrap cells. If you look at the sides of that, let's see if I can get the angle. That cell is okay. Now hang on, because I just discovered on a battery I have. Do you see the top of the blue battery? It is not flat. This battery, this is a pretty old battery. I've had this battery probably 6 or 7 years. And if you look right at the top, it has a dish to it. And you may or may not be able to see on the camera. Yeah, you can see it's puffing. This battery is shot. This battery will be disposed of properly. I will not use this anymore. This battery is going to fail. If I'm lucky, it'll just die. This battery is very likely on either at random or on the next charge cycle, it could explode or catch on fire. If you notice any physical deformity in your batteries, recycle them and make sure that you store and travel with them safely. Take your little LiPo bag when you stick it in there and stick it in the passenger seat so that you don't get a surprise. We just before the presentation here in the room had a demonstration, had a story by one of our producers here that said the exact happened. He was using some rechargeable lithium batteries in a device that smoked while he was driving down the road. And I see Doug says he has this problem with MacBooks. So
And
Surface.
iPhones tend to pooch up and screw up the screen.
Okay, so John says iPhones, when they swell, they screw up the screen. So that's all a good, if the battery's puffy, just consider that the end of the battery's life, please, and recycle it safely.
If you
Wonder why your device is starting to swell up and come apart, you probably should get it somewhere and get it repaired quickly.
Yep, that is the battery.
K2AD, he says he's got a problem with MacBooks. The battery bulges under the Magic Mouse pad.
Yeah, so those are all examples of that. There are a lot of laptops that do have just film, especially these really thin devices. They don't have hard cases around them. The older laptops that had the battery in the back that attached and things, those were in metal case. But as devices have gotten thinner and lighter, there's no room for all that extra stuff in there. So that's something to watch out for. If you see something swelling and it's battery powered, it's probably time to put it in a safe place and put it out of its misery. So, okay, back to the presentation, please. All right, so we talked about this. Now, we talked about puncture and shorting. Those are two big hazards with these batteries. LiPo being the most sensitive to this, but shorting all lithium chemistries, and that high energy density is it can pump an amazing amount of current out of a very small battery when they are shorted, and puncturing them causes essentially an accelerated chemical reaction doing the same thing. It's almost the same as basically a short. So they can, there are some tremendous, if you go on YouTube and want to see some of these failures, the failures of these batteries are just, there are some really creative folks out there with a lot of time on their hands that have proven a lot of these tests with nails, chopping through these batteries with circular saws and stuff. It does not end well. And they did that expecting it. If it happens while you're driving out to across the country or out to the field, it's not such a good thing. So please heed the safety warnings. Don't try to get one more use out of that battery. That blue one is going straight in recycling as soon as I get home. All right, so storage safety. We talked about that in the cans. I mentioned earlier about the shrink wrap versus the hard case versus the metal case cells. If your application allows it, use a metal case cell pack or a hard case cell pack. If the weight is really a problem, you can absolutely use the shrink wrap, but that's just, increased safety factor. All right, let's move on a little bit to discharge, because there are special rules for discharge on these batteries. But there's also, this is where the lithiums stand out from the other batteries in a big, big way. And let's talk about, there's a slide coming up on this one. The lithium batteries should be stored partially discharged. I prefer 40 to 60%. I think that encompasses most of the ranges of all the people arguing about it out there. And I have seen manufacturer numbers range from 40 to 60%. So that's what I shoot for. Here's the good news. If you use a charger like these will actually calculate it for you. You can discharge. I'm about to tell you not to use these chargers for discharge, but if this is all you got and you're willing to accept some of the consequences, these will safely discharge to proper levels, and you don't have to worry about it. You just say storage and put it in there. I talked about the balance, right? Lithium have fewer charge-discharge cycles, so you really need to look at your use of the battery and decide, what am I going to do? Am I going to discharge it to storage every time I use it? Most of the ones that I keep at storage levels, I use the 2-week rule. If I'm not going to use the battery again for 2 weeks and it doesn't need to be ready at a moment's notice, I'll discharge it. If I'm going to use it within a 2-week time period, I'll probably store it fully charged. The time it takes off the battery life is not that significant that it's going to make that much of a difference. So, personally I use 2 weeks, but you have to make a little bit of a decision. I think this falls into the HT, the go bag thing as well. What's your personal decision? Are you willing, able to, charge? Maybe you really want to get every last little ounce of life out of your lithiums for your HTs, and you store them at storage potential, and you have an alkaline pack, and you know where you're going. Your alkaline pack will run the HT adequately until you can charge the lithiums in your car. If you want to get that complicated and stuff, that is absolutely possible, but it's a personal choice. I would personally just choose to leave them full. Okay, discharge. You'll see the numbers are pretty significantly different here. Lipos and the lithium chemistries lose about 20% of their capacity in a year versus that 5% a month that most lead acid. And lead acid gets worse with temperature variations. So this will lose 20% of its capacity in a year if it's left fully charged and kept at room temperature. There's a number right there that should help you with that personal decision about how you want to make the battery, if you want to store them. 20% in a year is not, in most cases, probably something you're still going to get, as John said, 3 to 5 years out of that battery, because you're not going to leave it. You're going to use it sometime in that year, so you're not going to lose all of that 20%. You might lose 10%. So if you lose 10% of it, you probably get 5 years before the battery becomes too little capacity to be of use. Now, remember I said don't store them hot? Look at that second bullet. 40% of its capacity in 3 months if it's kept at 140 degrees. Now, where are you going to keep it at 140 degrees? You might keep it in your trunk in Phoenix. That's going to kill those things. Your trunk in Denver, 130. Good point, John. So, you can store them cold if you bring them up to temperature. Cold will not kill them like the heat will. The heat will just massively accelerate the self-destruction of the battery while it's sitting there. As I said, I use the 2-week rule for non-critical to-go batteries. And all my HTs and things like that, I keep at 100%. Okay. I just mentioned how this charger is smart enough to set the proper voltages at discharge. This charger that we use here, this blue, the model charger, if you look at the face of this charger, it says that it has the capability of charging between 100 milliamps and 6 amps, but the discharge is from 100 milliamps to 2 amps. Now, I do not know what the schematic of this particular charger is. However, I have been through many of these hobby-type chargers that have a discharge, especially the reduced capacity discharge in them, and blown these chargers up over and over and over again. My belief, and some of them do publish their schematics, lots of them do not use proper heat sunk resistors to dissipate the energy, and instead they pulse width modulate the same output transistors that are using for charge. They just PWM switch that to ground, and that's how they generate a load to discharge the battery, and that generates tremendous amounts of heat. And none of these things have proper fan cooling and things like that. I have fried so many chargers trying to use them as dischargers. It's not worth it. Dischargers are dirt cheap, so go buy a dedicated discharger. Now, here's a couple I've listed on the page. I have all those. We talked about the CBA, the Computerized Battery Analyzer. This thing is a resistive charge. It will safely discharge the battery. This will not balance discharge, but it will safely discharge. remember I spoke of balancing in charging. Well, it's just as important. If you're going to discharge to storage, you need to balance discharge and keep your cells flat. So you can use something like this. You can use something like that in a car headlight, again, even with a lithium. But you need to watch the individual cell. There are so many ways of doing that. These little devices, these two simply are voltage checkers and alarms. You can set the alarm voltage for any one cell to fall below. This one actually is a balancing discharger. When you're discharging your battery with a headlight or some type of load, this will watch the individual cell voltages, and when it gets close, it will add about 150 milliamp load individually to the cells to balance them out. These really work as simply as this. By the way, I think you can buy these types of ones. I think I bought a 10-pack of these for $4 on Amazon. So they have a very large alarm. 4 cells. It's reading total pack values. Cell 1, 3.17, 3.18, 3.17, 3.17. You can program these as an alarm. If you're using just some non-smart discharger that doesn't do this for you, you can set this to go off when the first cell reaches the low voltage alarm. For $9, you can buy something like this. Another RC, it's called the LiPo-PAL, works with all the lithiums. And this one, if you look on the screen, it's got each one of the cell voltages, and then I can't see myself. Is one of the V's flashing on this one?
Yeah, the one in the middle.
Okay, see that cell is 0.1 volts higher. That flashing V, this thing is now balanced discharging this. There's a 100 milliamp or 150 milliamp load on that one. And as it's pulling that one cell that's got a 10th or 100th of a volt higher than the other ones, it's actually discharging this, and then it will stop as soon as, there it is, and the V went solid. This pack is now balanced. So you don't need really expensive tools to treat your batteries right and do things safely. This one is just phenomenal. This discharger, which I think is under $20, has little halogen bulbs. I think these are 150 watt halogen bulbs. And when you hook this one up, this is a smart discharger that'll do each of the cells. I use a heat sink made by Ball, or Atlas, I think, because those bulbs get very, very hot. I hang my bulbs in the glass jar. And when you connect this battery up, you connect the balance. This charger is smart enough to disconnect. And then I hook the bulk charge ports up, and I set what I want my discharge voltage to be. In this case, it's and let's see, I think the discharge voltage. I hit balance here. There we go, and you'll see the balance icon. You can see from here this one's already at storage, but you can see it alternately applies different amounts of load to get the cells down, and then it's balancing each of the cell voltages with a very small load until it gets to the target voltage. The advantage of doing one of these is that batteries naturally, when you put a load on them, will discharge, and when you remove the load, they'll recover a little. This thing will actually stay and put a smaller and smaller and smaller load until the battery just sits right at your storage level. And again, this is less than $20. Safe, it's got both heavy and light discharge with balanced discharge. The voltage range makes it, you can set it so that it's compatible with any of the lithium chemistries you hook to it, and that's all there is to it. So you just wait until all the bulbs are out. This is there, and it stops bouncing around, and then you put your battery away. So for these types of things, now This is not a balanced charger, however. This is an excellent discharger. This is the same, you know, this one is actually computerized also, and you can track your capacities and things. This is Sky RC, and when you hook this one up, you can set your discharge current and run it down, and it will stop when it reaches it. Because this one doesn't balance, if you hook up the LiPo pal at the same time, which we can do here, that combination right there will now heavy discharge the battery with a proper resistive air-cooled load to remove the bulk of the charge towards storage. And then when it stops and it gets very close to the end, the LiPo pal will balance each individual cell with a 100 milliamp or so load until it's at perfect storage. These tools, these are a little more expensive, of course, than the light bulbs, but these tools are a good investment. Just pick one set and do the investment, and you will stretch these packs' life out. This pack was built in, I didn't label that one. This pack was built April of 2018. I build my own packs, so I tend to put the dates. Whether you build or buy, I put the dates on them so you just have a general idea of how old they are. I just cycle these. I do these once a year. I cycle these no matter how often I'm using them. I do a full capacity test on all these batteries. This was April of 2018, and I just did the test over near the Christmas time, and this one 2.5 years later is still sitting at, or 2 years later is still sitting at about 92% of its original capacity. And I use this pack maybe twice a year, you know, so they last if you store them properly. So back over here to our discharge stuff. Just went over some of the specials, reasons why you should use a balanced discharge and things like that. Over discharging a lithium battery, depending on the level, even one time can destroy the battery forever. Question?
Zero SW had a question. He says, some of my packs have battery management system boards instead of balance connectors. Is the BMS doing the balancing?
That is correct. And so that little circuit board I showed, that little round circuit board, that's a very simple one. Some of the packs have a full BMS battery management system in there. Yes, exactly. That's exactly what it's doing. That is doing the balancing for you. It's when the bulk charge comes in, it's shutting off each cell when it gets to the right place, protecting it from overcharge and making sure that the current going into it is proper. So yes, a battery pack that has a built-in BMS, and you will find, excuse me, those are available on all types and sizes of cells, but they're very common on much larger cells. So you'll find the BMS method is usually used with big, large cells more often, although it's available for anything. Is that, yeah? Okay, over discharging, I said you can just absolutely destroy a brand new pack by taking the cell. If you take it down below the recommended level, you can kill it forever. They're very sensitive to that. You won't always. It's not a guarantee, but it's a pretty good shot that you're going to do some very bad damage to the battery by over discharging. Just like charging, don't leave it unattended. If you're going to discharge, put it in your LiPo bag or your ammo can or your whatever your fire safe thing is. When the battery's being charged or discharged, the same hazards apply. So there's a chance of anything bad happening at any time. Just pop it in the bag and keep it. That'll be a much safer way to do that. Now the other thing to talk about is using a safe discharge rate. What is a safe discharge rate? These lithium batteries have crazy capacities on them. This one I'm showing on the screen right now is a 5 amp hour battery, but it is rated at 50 C. So you can safely discharge this battery, and there's caveats. Sometimes you can discharge them from full to dead. Sometimes there's a time limit on this. You need to look at the battery spec. But ignoring that spec for just a moment, this battery will discharge safely at 50 times C. That is 250 amps on this 5 amp hour battery. And they will deliver it. That battery will deliver 250 amps. Is that a good way to balance, to bring your battery to storage? No, it is not. The reason a battery is designed for something like that is it's mostly inrush current. If that hobby battery is running an electric motor in your airplane and you slam the throttle on full, there is very likely 250 amps that may run for a period of time. And then once it spins up and the friction losses and everything come down, it's going to taper down. But there are batteries, if it's not designed for that kind of current draw, that type of current, attempting to draw that current can cause the battery to fail. These are designed for that. Does not mean, it is typically not a constant current rating for the life. It's usually like a 1, 3, 10-second rating. It's not, so when you're discharging for storage, pick a reasonable rate. This battery, you could discharge this battery, the bulk discharge, at 1C, 5 amp hours, right? And it's going to discharge in an hour. It's not even going to take an hour because they don't hold as much energy as they say. So it's going to discharge at a pretty reasonable rate. And I think that's actually the end of the presentation. To briefly wrap up here, lithium chemistries are amazing batteries. We know, we use them. We've been using them in laptops and HTs and on all these things for years and years. You rarely hear about those batteries failing. And occasionally you do. Occasionally there's a laptop that smokes on an airplane while people are traveling.
They have safety bags on the airplane now too.
They have safety bags on the airplane, and those devices are built with so many safety things in them to contain, even if the battery smokes, to contain the fire and explosion, etc., hazard. So it's to minimize it, right? These, if you have these little lithium packs sitting on your seat, nothing's going to contain it, and it's going to catch your seat on fire while you're driving out to the location. So please remember these. Remember our fellow ham here in Colorado that lost part of his ham station because the battery burned up at night. Spend the $9 and get a bag and store and charge and discharge in there. Is there questions, Mark?
There was a couple battery scenarios from Brian, K0 FBS. Number one, base station and shack for backup power with a auto transfer switch charger like the Astron BBM30 or West Mountain Radio power gate. What type batteries and how to manage it over the course of the year?
So you're probably we're getting into opinions here a little bit. Certainly there are lithium batteries that will fulfill that role, but to be honest with you, for a price performance aspect, you want to use, back up your ham shack and something like that. An AGM sealed lead acid battery is probably going to be your best price performance break for something like that. It's capable of delivering the type of amperage, and then put a smart temperature 3-state temperature compensated charger on it and leave it on all the time.
The second one from Ryan as well, it says like events like parks on the air, the batteries need to be portable but carry a short distance and stay put until events is over and used 2 or 3 times a year.
Yep. And so was there a question?
I don't know if that was the comment or the question. It was just this number 2 is the battery scenario.
Okay, so that scenario fits. It fits either any of the types of batteries fine, but it's actually a very good lithium fit. And the reason I say that is, lithium is small and light, right? And so if you buy your little charge bag to carry it to and from the park on the air, while it's in the car, and then you buy Buy one of these little these cheap little balance voltage monitors and set it up. Set it at 80% of the capacity, right? So look up the full voltage of the cell, the dead voltage of the cell. 80% down is, per cell voltage. Program it into one of these. It's got a bright alarm on it, a real loud alarm. And then just leave this plugged into the battery the whole time you're using it. I do that on soda trips. I plug my little balance board, my little alarm board in. And if I'm sitting there with my headphones in and working a, CW or working a station, I usually carry 2 of those little 18650, a little bigger than AA sized packs. And if I'm operating and the pack gets too low, this thing screams at me and I just change batteries. And I take it home with 20% of the charge in it. It'll sit like that for days without really any problem. And then I just make sure to charge it back when I get home.
I'm going to go back. Toward the beginning, I know Ted Klein had one that we didn't answer earlier. But he was looking for you'd mentioned some schematics from ANA Engineering Charger. There was kind of a link with aaengineering.com. And he said nothing was found on that site.
I was on it last night, and I'm pretty sure it's still, one moment. Okay, so the website is a-engineering.com. And if you look on the left side of the page, there's a 1A schematic for the 1 amp charger and a 5A schematic for the 5 amp charger. There's the schematic for the 5 amp charger right there. And you can see at the center there is the unitrode chip, and there's a couple of resistors and capacitors, and then up at the top of there you'll see the drivers that are set up to handle all this battery current switching. So all of that's there. He also has on this web page the component layout. There's some pictures. Here's the parts lists for the chargers. So everything's here. Even though you can't buy it from him, you can still build it yourself. And the part layout would even help you design your own board if you wished. There's all the physical layout of the parts.
Okay, and I've got another question, but I want to remind everyone, you can either type questions in the chat, or if you come off a mute, you can ask your question directly. James will be able to hear that. On the chat from Chris Truby, for ham shaft usage, 2 6-volt AGM 200 amp hour deep cycle in series, or 1 12-volt deep cycle, which is better?
The 2 6-volts in series will give you more energy than the single 12, and that's been a long proven tradition. 6-volt batteries are very commonly used. If you open up any electric golf cart, most of those large current draw devices, the 6-volt battery in series is almost always, they're usually more expensive, but they will last longer. They will give you more energy than, or a LiFePO. And like it used to be that an equivalent energy density LiFePO to those was a bank breaker, and that has changed a lot.
Buy cells on eBay, it's almost the same price.
Cells on eBay, yeah. I mean, it's getting to the point where you can actually put a couple hundred amp hours in your RV for a couple $100. It's a huge change.
Okay, Willem pointed out, I must have missed something here. I must not had enough coffee. And he goes, bottom line, don't trust a battery further than you can spit a piano.
Yeah, the batteries are something we rely on heavily, so they're absolutely going to be the thing that fails when we need them the most. So it's never a bad idea to have some spares.
That's all the questions I have in chat. Does anybody else have some questions with James? Again, feel free to come off of mute, and you can ask your question directly. And I know Greg Pettis is pointing out he appreciated your presentation, and had given us some thank yous for us working behind the scene.
Yeah, thank you to the team back here putting this all on. And if anybody has any questions, I do not work in this industry. I am not an expert in these things. As I mentioned at the very beginning, I learned about all this stuff and set out under massive research projects to improve. I was spending so much money on batteries that were failing at an alarming rate. I just decided to invest in the time in learning to figure out why and how to prevent that from happening. So, I hope the information that I've learned and researched and been able to pass on is useful to folks. Certainly happy to answer any questions. You can reach me, with the contact addresses. My QRZ address is good, or ki0kn@arrl.net. Also, I believe reachable with contact information on the RMHAM page.
Correct.
So, yeah, thanks everybody for listening. And
we'll have your presentation up
Thanks, James.
this afternoon.
okay, presentation will be posted this afternoon, John says.
Thank you very much, James. We very much appreciate it. And I just wanted to remind everybody, our speakers put in probably 10 times the amount of hours preparing for these presentations compared to the actual time it takes to actually do it. So we very much appreciate all of the time and effort they put into it. Also, on January 19th, so 10 days from now, Chris, K0SWE, is going to give RMHAM Tech Talk at 7:30 on Tuesday evening on how to program your radio with Chirp. And then on the 23rd of February, not in May as I said originally, but in February, Gary Sutton, WB5PJB, is going to give an overview of WinLink and whether you should use it as an RMS versus point-to-point. Our next RMHAM University is actually NerdFest, which is a month from now. So if you're interested in giving a short talk during NerdFest, basically just sort of a bunch of different topics, it's all going to be by Zoom, so you don't have to come in for that. But we're looking for people who are interested in giving a short talk on some technical topic. We very much appreciate it, and thank you again, James, for doing today. It was very interesting, and I learned more about batteries than I ever knew. Thank you very much.
You betcha.
Okay, everybody. I just wanted to give you a quick little overview of what it takes to do this. We have Rob over here at our second camera, James standing up in the front. Here's Mark, who's running as director. He's actually controlling all of the different camera shots. This laptop over here runs what the presenter sees, so they can actually tell what's going on. But all of the hardware necessary to make this happen is quite a bit of gear. And I'm running what's called a Steadicam, and I'll switch to it here, and you'll see exactly what I've got as soon as Mark pushes the right button. There you go. That's a Steadicam. We've got a bunch of wireless microphones. Everybody's wandering around and can answer. Over here on this display, they're watching to see exactly what's going on. So every time you guys have a question, we put it on this screen, and we grab a microphone and interject it right into the middle of what's going on. But definitely not a small feat. Takes a lot of hardware, a lot of time, and all to try to get this to where you guys can see it. Thank you very much for attending. If you guys look for the presentation to be posted in the next day, and I'll also have the video up on YouTube just as quick as I can. Thank you guys for watching.
Thank you all.
Thanks, guys. Good job. Stop it here. Yeah, click stop stream. Stop recording.